You've definitely heard about this. The 2015 detection of gravitational waves was celebrated everywhere as this massive breakthrough in physics, a total confirmation of Einstein's genius. It even nabbed a Nobel Prize. But is the story really that simple? In this explainer, we're going to look past the headlines, dig into the actual evidence, and explore some really tough questions that other physicists are asking about what might be one of the biggest discoveries of our lifetime.
So get this. This quote is from physicist Sabine Hossenfelder, and she's describing the kind of reaction she got for questioning the official story. Someone told someone else to slap her. That is a pretty intense response for a scientific debate, right? It's a huge red flag that we're not just talking about dry data here. There's a real controversy, one where careers and reputations are on the line, and the story is way more complicated than you probably think.
All right, so before we get into all that drama, let's just quickly recap the official story. What exactly did the scientists say they found?
Okay, so what are gravitational waves? Well, Einstein predicted them over 100 years ago. They're literally ripples in the fabric of space-time itself. The best way to picture it is to imagine two super heavy things, like a couple of black holes, spinning around each other. As they get faster and closer, they send out these massive wobbles in space and time, kind of like ripples from a stone dropped in a pond.
And look, we've had good reasons to believe they're real for a long, long time. Back in the 70s, two astronomers, Hulse and Taylor, found incredibly strong indirect evidence. They saw a pulsar binary system losing energy at the exact rate Einstein's theory predicted it would if it were giving off gravitational waves. That was so big it won them a Nobel in '93. But the real prize, the Holy Grail, was always direct detection. And that's what the LIGO team announced in 2015, which got them their own Nobel in 2017.
So how on earth do you even detect something like that? The technology is it's mind-bending. A LIGO interferometer starts with a laser and splits the beam in two. Each half travels down one of these super long arms set up like an L. They bounce off perfect mirrors at the ends and then come back to meet up again. And here's the magic trick. A gravitational wave passing through should, theoretically, stretch one arm just a tiny bit while squeezing the other. We're talking about a change smaller than the width of a proton. But that tiny change is enough to knock the two laser beams out of sync. When they recombine, they create a disturbance pattern. And that disturbance, that's your signal.
It's an absolutely beautiful theory, right? An amazing piece of engineering. But despite all the Nobel Prizes and the media celebration, some physicists started raising serious questions. And they weren't questioning the theory, not at all. They were questioning the evidence that was actually presented.
So, what's the hang-up? What's the problem here? If the tech is so brilliant and the team is so smart, where's the issue? Well, all the critiques really boil down to some fundamental questions about scientific process and, what really counts as proof. And let's be super clear about this. As Sabine Hossenfelder says herself, she does not doubt that the detections are real. This isn't about a bunch of people saying gravitational waves don't exist. The issue is all about scientific rigor. It's about that but. The real question is the proof we've been shown strong enough to really close the case beyond any doubt? Okay, first up, let's talk about the plot. The first major issue is all about that famous visual, that graph from the very first discovery that was plastered everywhere.
Oh yeah, you've definitely seen this image. It's often called the banana plot because of its shape. It shows the frequency of the wave getting higher and higher, making this beautiful clean curve as two black holes spiral in. And then it just stops when they merge. It looked absolutely perfect, a textbook example of the theory. Maybe a little too perfect.
But here's the bombshell. Members of the LIGO collaboration are actually on record saying that the smooth theoretical curve, the one that fit the data so perfectly, wasn't found using their standard analysis algorithms. Instead, it was partly done by eye and hand-tuned for pedagogical purposes. Wait, what? Hand-tuned for pedagogical purposes? That basically means it was adjusted to make a clearer picture for teaching. For the key piece of evidence in a Nobel-winning discovery, that is a jarring thing to hear. And what makes this even more troubling? The silence. When asked about this, about how exactly that curve was fitted to the data,
Both the LIGO collaboration and the journal that published the paper have reportedly refused to comment. For a claim this huge, that kind of silence leaves a massive, unanswered question just hanging in the air. That's not how science is supposed to work.
Okay, so the questions don't stop with that plot. It actually leads us to an even bigger, maybe more fundamental problem. How can we be 100% certain that the signal they're seeing is from deep space and not just some weird, unexplained noise happening right here on Earth?
Okay, this is super important to understand. In science, the gold standard for confirming a discovery like this is independent verification. The best kind is a prediction. That's when LIGO sees a gravitational wave and tells astronomers, hey, point your telescopes over there right now, you should see something go flash. If they do, boom, that's powerful proof. But there's a much weaker form called a postdiction. That's when a telescope sees a flash first, and then the LIGO team goes back through their data and says, hey, you know what? We found a little wiggle in our data that matches that. It's just not as convincing because you already knew where and when to look. And this brings us to the one and only event that ever had a potential counterpart we could see. This was a neutron-star merger back in August 2017. So here's what happened. First, telescopes saw a gamma-ray burst. An announcement went out to the astronomy community. And only after that did the LIGO team announce that they'd found a gravitational wave in their data that corresponded to it. See the problem? This was a classic postdiction, not a prediction. It just wasn't that rock-solid, independent proof that science really demands. And this right here really shows you the incredible scale of the challenge they're facing. On any given day, LIGO might register maybe one candidate signal that looks like it could be a gravitational wave. But on that same day, it also registers between 10 and 100 unexplained noise events. The team calls them glitches. These are powerful signals, they're real disturbances, but they just don't match what the theory says a wave should look like.
So what do they do with all that junk data? Well, one source summarizes the process with this pretty blunt statement. The team has to, effectively, throw away any data that doesn't fit their model of what a gravitational wave is supposed to look like. Now, that sounds kind of unscientific, doesn't it? Let's use an analogy to understand why this is such a potential minefield. Okay, imagine I claim I'm a psychic. I tell you I can read your mind. My big guess is, you're thinking of an elephant. Now, if you were thinking of an elephant, I'd say, see, I'm a psychic. But for every single person who is thinking of a lion or a penguin or their car keys, I'd just say, nope, you're a glitch, and I'd ignore your result completely. So does that prove I can read minds? No way, of course not. It's just cherry-picking the one success out of 100 failures. And the concern is that without that independent, predictive proof, LIGO might just be finding the elephants it's looking for in a vast sea of random noise.
So, where does this leave us? It really forces us to take a step back and very carefully separate the hard evidence that we actually have from the expert opinions and even the hopes that surround it. So let's just recap the big takeaways, the key unresolved issues here. First, we still don't have a clear, transparent explanation for how that original plot was made. Second, there has not been a single independent predictive confirmation from a telescope. Third, the detectors are just swimming in unexplained glitches. And because of all that, we can't be 100% sure that the signals they are finding aren't just some unknown earthly effect that just happens to look like the real thing.
Look, most physicists, including the critics raising these questions, personally believe the signals are real gravitational waves. They want them to be. But as this quote reminds us, in science it's evidence that counts, not opinion, not belief. And the celebration of this incredible discovery may have simply run ahead of the rigorous, transparent, and independently verified proof that science demands. And that leaves us with a really fascinating question. How much certainty do we really need before we write a discovery into the history books for good?